Good morning, everyone. Welcome to week 7. So before mid-semester, we dealt with some preliminary concepts such as the forces, vectors, how forces can be combined, even some simple systems, whether they are one free body diagram or multi free body diagram, they are in equilibrium together. And we learn how to find out the conditions and apply them to the structure, find out internal forces to keep the systems under equilibrium. Now we start to move to more practical, more sophisticated, and of course more complex structures, that is a beam. And so with the beam, there are few basics and preliminaries we have to cover. The first thing is what is beam? What makes a beam different with a bar? So how do we know that something is a beam, something is a bar or two force member? The answer to that question, you should know, that is a bar or two force member can only become longer or shorter. Examples are individual members inside the truss structures. Okay, and many other mechanisms or machines or frames, they might have two force members, three force members. But the thing with the beam, specifically with the beam, is beam allows the transfer of the load from one support to another support by the action of the bending. So how does this help? So imagine that you want to pass over a river, and if you put a horizontal structure and then this is supported by both ends of the river, and so once something is passing over the bridge, the reactions develop at the two ends, and the beam is resisting deformation by the action of the bending. And that deformation, how do you know that? I mean, let's put all the mathematics behind a very simple um, hint. How do I know that something is beam when I see it? Okay, so imagine that this horizontal plate is made of a very soft material, okay? Something like a cheese. If that was very soft, how would you imagine this responding to the loads? Is this going to become longer, shorter, or is this going to change the radius of curvature? Radius of curvature is the keyword. Please take note. So this is what I mean is, if that is made of a very soft material, when you load it, this is easy to imagine, isn't it? You don't need any mathematics. You don't need it. Even it might deform like this. Okay, I'm exaggerating, but you can see the essence. That is the bending. The structure would change its radius of curvature. And then every structure, when you see it, it's a big decision to make. The first big identification to start with is this: what kind of a structure is it? If you can't classify it, the chances are you cannot solve it, right? This is a good example is a bookshelf. A good example is a bridge. A good example is an airplane wing. Imagine an airplane wing is a cantilever, but that cantilever, when the lift force is applied to it, it won't become longer or shorter. It changes the radius of curvature, right? So now you know that what the beam is, what makes a structure. This is not to do with the geometry, right? Geometry could be uniform, the geometry could be tapered or whatever. It's more to do with the loading. So we want to learn about the loading. What is so special about the loading? I mean, it could be the case that a beam is subjected to a point load. That's too simple. And then we know how to find the reaction if this is a point load. But the thing is, with the beam, the chances are loads are distributed load. What does that mean? Good example of that is the bookshelf. We don't have one single heavy book exerted at some point, but these are a group of books. So in averaging, we can represent the effect of that group not as a force, but as a force intensity. Look at the unit of that. This is from now on, this distributed load, we use a symbol. Remember that symbol, we call that W. W is intensity of the load. And then I put an X in front of it. What does that mean? It means my X in a beam is the longitudinal direction. And vertical direction could represent many different things, right? So don't get confused with this one. Horizontal is always X. The vertical represents the distributed load, W of X, or it could be a vertical displacement, Y, or it could be some internal forces. You want to show that internal forces are not uniform. Internal forces, we don't know what type of internal force develops inside the beam. We already know that when there's a bar, internal force is either tension or compression. One single load. But with the beam, I'm going to tell you about the internal forces soon. But before that, just for now, consider that the vertical axis is used to show that how these forces or these loads are distributed. The unit for that, this is intensity. Could be Newton per meter, Newton per square meter, depending whether the problem is a two-dimensional, three-dimensional. And well, we are not familiar with that type of loading, are we? I mean, if I put some point load here and ask you find the reactions, perhaps you make a diagram and do it. But if the forces are distributed, how can you solve? How can you find the reactions? So listen carefully. This is a very simplifying step. We're gonna learn that today. That simplifying step is a distributed load is equivalent to one single resultant. But then the question is, with a distributed load like this one, I know what the resultant is. The resultant is the area under this function, whatever that function is. This function is constant. This function between here and there, x between 0 to 1.5, what is the function of W of x? Anyone can say? That is 30 Newton per meter. That's constant. It doesn't change with x. If that was a line, you could have expressed it as the equation of line. If that was a distributed like a quadratic, you would have described it as a function of x. But here, it's not a function of x. It's uniform. The same is between x equal to 1.5 to x equal to 2. That is W of x is equal to 50 Newton per meter. All right, how do we deal with that? I mean, when I say deal with that is I am interested to find the reactions. So I have to get rid of that creator. That is not known to me. Let's replace this one with one single resultant. That single resultant, we call that R of R. Hello, Jackie. So that single resultant, I call this R. That's the resultant. But the question is, where should I put this R? Should I put it at the beginning? Should I put it at the end? Should I put it in the middle? Is there a general rule to know that where this equivalent of the distributed load should be located? So that we call this line of action. So line of action measured from 0, we call that X bar. So this is, I mean, mathematically we can show this, but X bar can be found either from that formula or from the concept behind it. The concept behind it is this is the one element of here, the unit is force, because if you take dw multiplied by dx, the unit is Newton. So that Newton multiplied by the typical distance from the zero, that is moment. So the very same thing in the denominator is a force, moment divided by force, that is a distance. So that is the physics behind it. So anyway, you've seen that formula in calculus, in high school, we discussed that before. For this subject, don't worry, you only need to apply that as a recipe. Okay, so you'll be given a function of W. Do you know how to integrate? I hope you do. Not in most cases, because these could be some primitive shape. You already know the integral, something like rectangle, triangle, and all that. But the concept is, the most important concept is this complex system. We have to simplify it with that system. Why? Because this is easy to find the reactions. That one, the finding reaction is not easy. This is only for that step. Once you find the reaction, then it goes back, you roll back this to the complex shape. Okay, I explain that later, but for now, all you have to remember is, okay, I've been given a beam. How do I know this is a beam? I just visualize. This is made of a cheese, and under the load, it's going to change its radius of curvature. So that's the beam. Second, I've been given a W of x, function of distributed load as a function of x. How do I find the resultant load? The resultant load is integral of that function over this interval. So in another word, R is integral of W of x dx between 0 to L, whatever the length is. All right? So that is FR. This is the resultant. And the second thing is line of action. Where do I place that? Do I put it here, here, in the middle? The answer is you have to use that formula. For the simple case of a rectangle, that x bar is L by 2, right? It makes sense. If that was a rectangle, right? So this is uniform, and that resultant load should move toward the center of area for that shape. So in general case, this is the center of area for that shape. You've been told that in calculus, in prior mathematics. So, okay, the next thing is that we know an integral can be represented as a summation. I can break that. If there are multi-loads, I can break that into summation, something like summation of x, W of x, divided by summation of W of x. Okay? So that, I give you some examples soon, but for now, that is all I just summarized from a prior case. And that explains why this is the center of the area. All right, so that quizzes, we did them during the class. So in this case, the resultant force is the area, and the line of action is centroid. So here, let's find out actions. That's a very simple case. So in this simple case, the steps are, first, you need to find the resultant force. So the resultant force here is Fr, which is the area under this curve. So that is 400 Newton per meter multiplied by 10 meter. Look at this, meter and meter, they cancel, and the answer is 4,000 Newton. That makes sense, doesn't it? So 4,000 Newton, where should I place it? Should I place it at the beginning, right in the middle, because it's uniform, right? So I know the centroid of that rectangle is at 5 meters. So x bar is equal to 5, and Fr, that is equal to 4,000. So that was simple. And next question, what are the reactions now? Just, you should say that very comfortably. If this is 4,000, the problem is symmetric, the load is symmetric, the reactions are going to be equal. So 4,000 divided by 2, the reactions are 2,000 here and 2,000 here. Correct? Okay, that was just to warm you up. Let's get with something more complex. So here you have. In this case, the distributed load is a triangle, and we want to find out first, we want to find out the resultant load. Second, we want to find out the line of action. Third, we want to find the reaction of the support. Okay, the resultant load is the area of the triangle. I mean, I can find the equation of W of X, and from that, I do the integration. That is a mathematical practice. We do that for more sophisticated problems. With a simple problem, you don't need to do the integration. Simply, with a triangle, you know how to calculate the area of triangle. Who can tell me what is the area of this triangle and what is the unit of that? So sorry, this is a very it's not properly written. That is 100 times x. This is not multipliable. This is 100x. This is badly written. So 100x means that x equal to 0, w is 0. At x equal to 6, this is 600 newton. So if you try to drive that equation, this is the equation. And to be precise, that is minus. This is not plus. Because the forces are acting downward. The forces are not acting upward. So this is minus 1000x. So actually, this is minus 600. This is 0 here. But anyway, the area of that triangle is the base multiplied by the horizontal line. So that is 600 times 6. So FR, that is 600 Newton per meter multiplied by 600 meter, 6 meter. So that is 3,600 Newton. So meter cancel, and the unit is Newton. 3,600. Where should I place that? This is the resultant. Okay, very good. So the centroid of the triangle is 1/3 of the. So 1/3 of 6 is 2 meters from here, or 4 meters from here. So in terms of the symbols we have, this is called x bar. X bar is measured from the x0, this is x-axis, and this is W of x. So x bar is 4 meters. All right. Now that you have this one simplified, to find out the reaction, all I need is this. So instead of that triangle, I replace that with 3,600 here, and one reaction here, one reaction here. That is 4 meters. This is 2 meters. And that is AY, this is BY. How do I find them? Easy. Simply, I take net rotation with respect to the A equal to 0. That is minus times 4 plus By times 6 equal to 0. So from here you find By, and then net forces in the y direction equal to 0. That give you Ay. Or you can take rotation with respect to the B to find Ay. Make sense? Okay. Now, this is more challenging. Can I ask everyone to give this a go before we try that together?
So the previous part we trying to find the what's it the force,
resultant
force,
line of action,
and line of action, as well as the reaction.
That's what you do with the beam.
Yeah.
If you give a beam that's complex, you have to simplify it. How do you simplify? You replace the distributed load with the lump load. Why? Because I'm interested in reactions. Why am I interested in reaction? Because after reaction, I need to go and find the internal forces inside the beam. That I haven't told you yet, but we are preparing for that now. So if you want to do the same thing here, there is a trick to avoid the integration. I mean, you always can. Let me tell you the standard way of solving this and a shortcut. So if I want to do the standard way of solving this problem, that is not. How many steps are there? The first step is to find out FR. So FR in this case, that is the area of this shape. How do you find the area of this shape?
Oh, divided into two shapes.
Yes, exactly. That's the key point to solve it, right? So, in another word, you want to. This is a
One rectangle, one
yes
triangle.
truncated triangle. What is truncated? It means it doesn't have an apex. So you draw a horizontal line, and now you've got. Let me pretend there are two type of load here. So this is W1, W2. W1 is 0.5. W2 is
2.0.
no, not 2.5.
2.0.
2.0. 2.0 to 0. And is there another way of doing this? Yes. Another way of that is, how do I find equation of this line? How do I find the equation of this line? Anyone knows? If I have this line as W of x, then I simply can integrate it. That technique is not difficult, but I teach you that later when we get into more complex distributed load like quadratic, cubic, or functions. But in this case, how do I get rid of the triangle? The triangle, I call this FR1. So this is area 1. This is area 2, right? So FR1. And what about the rectangle? Rectangle, so with that, I call the line of action X bar 1. And with the rectangle, I call this FR2. And then the line of action for that is called X bar 2. Okay, let's find out FR1. Who can help me with FR1? Area of the triangle. Base multiplied by the side, that
1.5.
The
triangle.
Yeah,
triangle.
2 times 3 divided by 2, right?
Yep.
That is 3 Newton. And what about FR2?
1.5.
So that is 3 multiplied by 0.5. That is Newton meter. This is meter. That is 1.5 Newton. Oh, sorry, kilonewton. Okay, and who can tell me what is X bar 1? That is the centroid of this triangle with respect to x0 is here. So that is 1/3 from the base, right? 1/3 from the base. The base is 3 meters. 1/3 is 1 meter. So X bar 1 is 1 meter. Everyone can see that. And what about X bar 2? X bar 2 is the centroid of the rectangle. So this rectangle, this is area of 2. The centroid of that is 1.5 meter, correct?
1.5.
Now, let me bring the equation we had before, and I'm trying to reinvent that equation. So what do I mean by that? This is, all right. First question, how do I substitute two forces with one single force? I mean, another simplifying step is if I replace two vertical forces with one force. Well, how do you add two vectors, two parallel vectors? You just add them together, right? So the net resultant force, that is equal to FR1 plus FR2, which is 4.5 kilonewton. That was easy. Now, a little bit challenging question is that FR1, it means I'm getting rid of these two forces and replacing them with one single load. So these two forces, I substitute them with one single big load, Fr, or sigma Fr. That is the sum of the two forces, but that single force, it has a single line of action. Where should I place this resultant? That I call this X bar. Where should I put X bar? So watch this carefully. That is a reinvention of the very same formula. The formula I gave you in the lectures, that is the formula. I'm going to break that into summation. We know that integral can be simplified to summation. So I simplify that X bar is equal to summation of xi Fri divided by summation of Fri. What does that mean? It means
The moment over force.
X bar 1 Fr1 plus X bar 2 Fr2 divided by Fr1 plus Fr2. And from unit perspective, it makes sense, doesn't it? Because the numerator is kilonewton meter, the denominator is kilonewton. So that is equal to 1 times 3 plus 1.5 times 1.5 divided by 3 plus 1.5. So here I can find out, I mean, eventually, watch this very carefully. So I say that this structure is first simplification step. The first simplification step is I get a beam with one load here, one load here. This is Fr1, this is Fr2. And then I simplify that further. The next simplification is I get rid of both forces and replace them with only one single force. This is sigma Fr, or the summation of F, and it has one single line of action, X bar.
So in order to avoid doing integration, we can use some summation instead.
Provided that the shapes are primitive. Primitive shapes are rectangle, circle, or maybe.
Oh, if it's in the curve,
Yes, you do integration.
Yes,
you do integration. These are shortcuts. You can't always, special cases. Special cases. I show you some examples of general case. So first, if you know the special case, it becomes easier to understand the general cases. Okay, so that hopefully, so let's try this one. And then what is the eventual question? The final question is you want to find out the reaction of the beam. But before you find the reaction of the beam, you need to simplify the structure. So can someone tell me, just in steps, not in numbers, in steps, how do we find the reactions here? Well, we got two rectangles, two distributed loads. We need to simplify them to point load and line of action. And once you have it, the 2 point load again can be merged together with one single resultant, one single line of action, and then you end up with a simple beam, and with the free body diagram you find the reaction. These are the steps.
Okay. Can I see the answer?
Yeah, yeah.
1.88.
That is divided by the distance, which is 6. That is 1.88. This is the final answer. This is the x bar, total x bar. 1.88 is almost passing the middle. The middle is 1.5. This is here. So eventually you would put net force, sigma fr, and x bar. So this x bar is 1.88, and that total is 11.
Oh, so we plus the external force as well, right?
Yeah.
Again.
Yeah.
So all forces are included.
These systems are equivalent. Equivalent, it means when instead of finding reactions from that complex shape, I find the reaction from the simplified shape. Both of them are equivalent, the reactions are the same. I mean, for a more detailed analysis, they are not equivalent, but for reaction purposes, they are equivalent.
I thought we only include the one in the shape.
Yeah. I'm going to give you an example. Don't know if that confuses you more or that doesn't help. If you have a membrane, you know what membrane is, right? If you have a membrane, and that membrane, you're looking at it from here. So if I apply a pressure, a uniform pressure here, how does this membrane deform? It deforms very smoothly, right? It deforms like that, correct?
Mm-hmm.
But very same membrane, if I simplify that, it means the membrane now has one single force here. How does this one deform? This one doesn't deform smoothly. It deforms like that, correct? It has a sharp. So that is why the simplification is not for calculating the internal forces, the deformation. The simplification is only to find these two guys. Once you find the reactions, you roll this back to where it was. So later on, when we are trying to find the internal forces, we can't use the simplified free body diagram. This is only simplification for finding the reaction, for finding the deformation, for finding the radius of curvature. That simplification is not forbidden. You cannot use it because they are not the same. Did I make it clear? Okay, later on, I explain this more. If you understood, good. If not, don't worry. Okay, now we've got a complex beam. When I say complex, the loads are complex. When you find a problem difficult, what do you do with it? You break it into a smaller problem, to mini problems. So here, how do I break it into mini problems? One mini problem is a triangle sitting here, another triangle is sitting here. So each triangle is substituted by a resultant force and a line of action, and then those resultants are merged together in one single resultant, and the line of actions are merged together in one single line of action. So let's follow the steps. The first step is let's replace the okay, first step is this is equivalent to a beam. All right, let's start with getting rid of that triangle. That triangle, I call this triangle 2. This one, I call this triangle 1. So with triangle 1, what should I substitute for the triangle? One resultant, FR1, and one line of action, X bar 1. With triangle number 2, what should I replace? I should substitute a resultant load FR2. And this line of action, I want to measure it from the same reference, from the same beginning, that is X bar 2. And then how do I mean, again, of course, here I've got a moment, I've got a point load here, and then I simplify that further. That is a beam which has one single FR and one single line of action. Of course, these loads are as they are. Okay, I've got the big picture. The big picture is clear. Let's do the calculation. FR1, that is the area under the triangle, the area of the first triangle. The base is 6 kilonewton meter. Multiplied by the span. Span is 7.5 meter. Divided by 2. And what about X bar 1? X bar 1 is the centroid of this triangle with respect to x equal to 0. This is my x-axis. This is my x-axis. And this is where x equal to 0. So X bar 1, that is 2/3 from the apex. 2/3 of 7.5 is what? 5 meter, right? And what about FR2? That is the area of the small triangle here. 6 multiplied by 4.5 divided by 2. And what about X bar 2? Please note that X bar 2 is measured from here, not from here. So 1/3 from this base.
Can I measure from B?
No.
No?
The coordinate system should be the same, because later on we want to merge them together, and that makes like that. Okay, so now the second centroid
1/3 times 4.5 plus 7.5.
Yes, 1.5 plus 7.5, that is 9, correct? 9 meter. Okay, now the resultant force, the total resultant force is FR1 plus FR2, and the net, the total line of action, that is X bar 1 FR1 plus X bar 2 FR2. And the denominator is X bar 1 plus X bar 2. So with the numbers, I show you the number. Yes, go on.
Shouldn't we include?
Well, these are just to simplify. Still, these force should remain here, and that moment should remain here. These are when you're finding the reaction. In your final free body diagram, this is your final free body diagram. This is, you have whatever you call them. This is O, this is K, for example. This is KY, this is OY. Right? So this is the final free body diagram. You have to include 500 kilonewton meter here. You have to include 15 kilonewton here, and you have to include FR at X bar. And then this can be solved. Okay, so now, then the resultant force, that is the total resultant force, is FR1 plus FR2. And the net, the total line of action, that is X bar 1 plus X bar 2. And what about X bar 2? Please note that X bar 2 is measured from here, not from here. So 1/3 from this base,
So the new position is the sum of the two force only, right?
Yes, that is you substitute. This is how you add the vectors. The vectors, you add them just because they're parallel at the same direction, you add them. But then the question is, where is the line of action for this net force? This is not at x1, not at x2, this is at x bar. That x bar is found from this formula. And that formula is integral converted to the summation. We converted the integral equation to summation. All right, now that you have the big picture, let's look at the numbers. So the number FR1, FR2, these are the calculations. And X bar 1, X bar 2, these are the calculations. And finally, X bar, which is the total. I mean, you can keep it like that. The free body dynamic, you can solve it like that, but you could combine these two into one single force. That requires a new line of action. Either way, you can either solve that free body diagram, which has too many forces in it, or you can combine these two forces together. That is up to you. Both of them give the same answer. Okay, now we finished with internal. We finished with simplification of the distributed load. That was just a preparation. So tighten your seatbelts. Now we are going to get into something challenging. You expect when a structure is subjected to bending, the radius of curvature changes. Okay, so that is easy to understand. If that crane, if that arm is made of jelly, just you pull one end, this is going to bend. It's going to change the radius of curvature. Not difficult to visualize, right? The tougher question is, all right, I know what the reactions are, but what type of forces are developing inside the structure to resist the reactions? So when you try to deform a beam, it is easy to find the reactions. But then this reaction from here, it has a journey to go to here. By the action of the bending, that bridge is supporting a car or a load which is moving around the bridge. So if you know that reactions, it doesn't mean that you know what is going on at each individual point. At each individual point, something different is happening. Some points over the bridge are more critical than other points. That is the key difference between here and between the truss. With the truss structure, you never ask a question, okay, if I take this load, 50 Newton here, 50 Newton here, if I pull it, make it longer, is this going to break here? Is this going to break here? Is this going to break here or here? All the same. The very same internal force developed everywhere. It doesn't change axially. But unfortunately, in the case of the beam, this is different. So you have to answer this question. When a truck is passing over a bridge, yes, okay, we know how to find the reactions. That's not good enough. We have to find at each individual point what forces are developing inside, because those forces eventually can make my bridge to break. And the question is, my bridge can break here, can break here, can break here. For every bridge, that failure point or that critical point is different. So it means you have to do a customized solution for every bridge, for every beam. Why? Because you want to know which point is the most critical point. If you know the critical point, what do? Either you change the material or you go and reinforce that part, preventing that from breaking. This is your responsibility. You become an aerospace engineer, you become a civil engineer. The final objective for you is, why do you analyze a bridge? You want to find out where is the critical point. You want to prevent disaster from happening. And you only can do it if you know the internal forces. And unfortunately, in the case of the beam, internal forces are not one, there are three. There are many internal forces. Some forces try to make this longer, some forces try to change the radius of curvature. Just in a nutshell, there are three internal forces in contrast with the bar, which only develops one internal force. That being said, the second challenge is the internal forces changes from point to point. It's not uniform, it's not constant. So you have to investigate all points within the beam to find out which point is the critical, and if you when you find it, it's easy to fix. So between now and end of semester, that's all we are doing. First, we reduce the distributed load to the point load. Why? Because that is easier to find a reaction. Once you have the reaction, then you ask yourself question, this particular beam, not with the simplified version, the complex one, what kind of internal force are developing at every single point? Okay, once you have it, it would be ideal if I have a graph. By looking at the graph, you simply look for the apex. What is the maximum of the graph? That means in the x direction, I know where the maximum internal loads are. And if there are few internal loads, which one is more critical? This is like three enemies have invaded the country. Which one is gonna be more critical, right? So are they comparable? The damage from this internal force, that internal force, this internal force, or the damages are the same? Or one of them are more critical? These are tough questions. We will be answering these questions between now and end of semester. Okay? Hopefully, Shabnam would take care of some of these things in the new year. I try to cover as much as I could before I leave. All right, so first question, when you see a beam, can you identify it? I mean, in normal high school, university, you've been told, look, solve this beam. How on earth do I know this is a beam? In real life, when you graduate, no one is going to tell you this is a beam, this is a bar. You have to make that identification yourself. And here, I'm giving you a very simple way of finding it. Please listen carefully. All right, answer my question. Why this structure is tapered? Why this structure is not uniform? Is this for making this more beautiful? Or is there a structural reason behind it? So why this structure has a thick section here, but a thin section here? That tapered shape, is there a reason behind it? Well, first of all, let's go to some more basic questions. Is this a beam or bar? My answer to this question, if that structure was made of jelly, if that was made of something soft, something like jelly, under the weight of the roof, this would have deformed like so. Change of radius of curvature, right? That's not difficult to visualize. This structure won't become longer or shorter. It changes the radius of curvature. Anyone can visualize that. Okay? So, with that simple visualization, you answered a very fundamental question. The fundamental question is that structure a bar or a beam? It is a beam. Why? Because the radius of curvature changes. Okay? Now, the next question. The next question is why that beam is tapered? Why here is thick and here is thinner? Why this gradually changes? Is this to make it more beautiful, or that's going to be a waste of material? If only for the sake of making things beautiful, you know how much in dollar value it costs or in terms of resources? The question is, there is a structural reason behind it. The reason is points here are more critical than points here. So some smart engineers, they decided to optimize the use of the material. I mean, they would have, it was easy for them to take a thick beam like that uniform, right? But that would have taken too much material, too much resources. They did some analysis like what you will do, and according to that analysis, they found that internal forces here are larger than internal forces here. And these internal forces change in some linear fashion. So this is a very smart design. They said, I put my material where it is more critical, and when it is less critical, I remove material to avoid consuming too much material. Okay, so let's give you another example. Here, can you identify which one is beam? That horizontal section, is that a bar or a beam?
Column.
No, not the column. The column, yeah, we don't cover column. Columns are complex, but I'm talking about that horizontal.
There.
Yeah, the horizontal one. Does this change the radius of curvature, or does this become longer or shorter? Change radius. So this portion here, that is a beam. And what type of load is that? It's a distributed load. So to find the reaction here, you have to substitute that distributed load with one single load and the line of action. And then you can find out this is like a cantilever. This is a cantilever fixed to here. And then that will change the radius of curvature like that. Okay? So that step only requires visualization. All right, so here we have an important observation. Why this concrete slab has grown a crack? So why did this crack? Some portions are not cracked, some parts are cracked. So to answer that question, just keep in mind that concrete is brittle. It is very strong in compression, but in tension, it is very weak, like a glass. If you pull the glass, it breaks easily, but if you push it, that will take the load. So during the bending, the internal forces are a combination of tensile and compressive. So what this observation is telling me, that in a beam, so this is a part of a beam. This is a part of a beam, and the portion which were subjected to the tension, they have grown crack. The portion which are under compression, they resisted the force. So this is very important for us. Whenever we are finding the internal forces, we should be able to say whether this is tensile force or compressive force. Because not all materials respond the same in a compression and tension. Okay, so that is what we can learn from this observation. And now that is perhaps a very small, very important slide for today. Why? I brought you a step by step to here. You know how to calculate the reactions, but the next milestone is to find out what are the internal forces. Internal forces, so this figure is claiming that if I make an arbitrary section here, then what type of internal forces are there? Because the next step is in my left-hand side free body diagram, which is this enclosure. Because I'm cutting this vein, it's going to bleed. The bleeding is not simple. The bleeding internal forces are not a tensile force. There are three types of internal forces in every beam. Three types. One, we call this the axial. We show that with N. So what does this C is telling me? It tells me that N is evaluated at point C. Point C is here. The second internal force is responsible for cutting it. This is called the shear force. This is like a scissor. With a scissor, when you cut a paper, what type of internal forces develop inside the paper? It's a shear force. So the second internal force in a beam, that is called V, shear force. The unit is Newton. For that one, the unit is Newton. What does this C is telling me? The C tells me that the shear force was evaluated at point C. If I evaluated at another point, that would be different. That would be another V. The third internal force is bending moment at that point. The bending moment is responsible for changing the radius of curvature. Okay, so as a recipe, memorize what I'm telling you. In every beam, there are three internal forces developing. The first one is axial force, and the symbol we use to show that is N. The second internal force is shear force. The symbol we use is V. The third internal force is bending moment, responsible for change of radius of curvature. We use the symbol M. Okay, so it's going to be a little bit confusing. Only way you can perfect it is by practice. But just listen before the practice. You remember, as a surgeon, you have the control. You can decide how to chop the patient. You want to chop the head, you want to chop the leg when you are making a free body diagram. A free body diagram, the question is, am I going to take the left-hand side free body diagram or right-hand side free body diagram? This is like you're a surgeon. You take a sharp knife, make an enclosure. That enclosure is your free body diagram. Free body diagram is your lab, is your microscope. Under free body diagram, you want to see the internal forces and the reactions. Now, the question is, if you decide to keep the right-hand side free body diagram, here I've taken right-hand side free body diagram, okay? If I wanted to take the left-hand side, my free body diagram would look different. That was, I not only cut it from here, also I'm cutting that from B. So B would develop a reaction By. And then over here, I have the very same force in an opposite direction, V of C, N of C, and M of C, correct? So here, I've taken the left-hand side, right-hand side. This is the left-hand side. No one told me I was wrong. Left-hand side, right-hand side. All right? Okay, now, it could be confusing. How do I know? I mean, in the case of a truss structure, I told you don't worry, assume everything is in tension. Once you find the answer, if the result is negative, you know that you are wrong, you change your assumption. But the very same thing could happen here. When I'm starting my free body diagram, how do I know I take on the left-hand side my shear forces like this or facing up? Which one is the standard? So that is simply, the next slide is simply a convention. It's not a big deal, but you have to remember the convention, because otherwise you find yourself confused between the sign. All right? The very same way in a truss structure, we assume everything was in tension. When we did the method of section, method of the joint, we assume everything was under tension. Later on, we could have been proven wrong. But we do the same thing here. All right. So whenever you are making a free body diagram, if you are taking the left-hand side free body diagram, these are the positive direction. The positive direction of V is pushing down. The positive direction of M is counterclockwise. The positive direction of N is from left to right. These are the default. These are the convention. Why? I give you some joke to remember this easily. That joke is, it's positive to laugh. It's negative to cry. Okay? So these type of loads make my beam to laugh. My beam laughs. This is positive bending. These type of things are making my beam to cry. That is negative. Okay, no, sorry. Here, this is positive. This is also positive. Why? Because that kind of loading makes my beam to laugh. Positive on the left-hand side is different to the positive on the right-hand side. That's the justification. Because both of them are making my beam to laugh. But whatever you remember from this slide is if you decide to do the surgery on the left-hand side, this is how you assume with the positives. You put the internal forces like that. If you decide to take the right-hand side free-body diagram, the positive are next.
So if the shear force going down is positive,
positive,
F1 is positive as well, right? Because it's going down.
yes. No. No. Just don't confuse that. F1 is negative, but all I'm saying is start with your free body diagram. Do you assume the VC pointing down or up? You assume this is be down when it is the left hand side. And if you find it like that, that V of C is positive. And if you take the right hand side, your conventions are reversed because this is action reaction. The very same. If the left free body diagram is correct, the right one is also correct. So that is the convention. You decide whether to take the free body diagram from the left hand side. Sometimes it's easier to take it from the right hand side. Sometimes it's easier to the left hand side. So either way, you know how to assume the direction of internal force.
If you take the left-hand side, then we have to determine the shear force first, and then if it's positive, that means that determines the moment as well. And
Yeah.
the moment.
If your answers become positive with that assumption, it means your beam at that particular section is laughing.
Then everything else follows along. The
Yeah.
moments and the
Yeah. If that assumption proves to be wrong, it means your beam is not positive beam, it's a negative beam. Like what you did in a truss. If the tension assumption was correct, the bar was going to be elongated. If that was wrong, it meant the bar was going to contract. So with the example, that clarified. But for now, if you understood it by 10%, that's good. Don't worry. Okay, so these are the most important takeaway from today's lecture. Inside the beam, how many internal forces in general, not always. This is the most general case. A specific case is maybe n of c is 0, still that's a beam. Maybe V of c cannot be 0, but n of c depends. Some cases could be 0 or not. Okay, the most takeaway from today, inside the beam, there are generally 3 types of internal forces developing. One, we call that N, that is responsible for the beam to become longer or shorter. One is shear force V, symbol is V, that is responsible for shearing the beam, something like a scissor effect. The third internal force is a bending moment, that is responsible for changing the radius of curvature. So in every problem, there are 3 enemies, or there are 3 invaders to the country. They want to conquer the country, they want to break the structure. Which one is more dangerous? These are like viruses, 3 viruses. The patient is the structure. Are these viruses going to kill it or not? Which one is more critical? You only know when you do the numbers. With the numbers, there is a trick to compare them. You can't quite compare them because bending moment is Newton meter, this is Newton, this is Newton. So to compare them is not simple. We will get into that later. But the step before that is we need to get the numbers first, and then we learn how to compare them. Okay, that shouldn't worry you. This is just the most general case. And in a general case, a complex structure is subjected to bending in all directions, axial load in any direction, shear force in any direction. But that is not for this unit, just this is the background information. That is how we do the internal forces. First, you need the reaction. If there are distributed force, you have to simplify them to lump load, and that makes finding the reactions easier. Now, I assume that at the start, you know what the reactions are. Okay, if you know what the reactions are, you make an imaginary envelope or imaginary cut. That is where you want to find the internal force. It's the left-hand side, right-hand side free body diagram. Then you decide whether to take the left-hand side, right-hand side, which one is easier to solve. And yes, in most cases, you need to know the support reaction beforehand. In some problem, you must get away without finding the reactions. You can find the internal forces. So you draw a free body diagram. In your free body diagram, it is very important. At the cutting point, this is like as a surgeon, you are cutting a vein. If you cut a truss structure, it only bleeds axially. If you cut a beam, there are three types of bleeding. One is end, one is shear force, one is bending. So in your free body diagram, you expose the internal forces as external. What it means is, this is like you're putting a plug to this vein, preventing from bleeding. You plug the second, you plug the third. That is the concept of exposing internal forces into external when you are making a free body diagram. All right? So N, V, M, these are the three types of exposition. So before cutting them, you don't have to include them in free body diagram. But once you cut, your free body diagram should be self-contained. It should be independent from the universe. To make that independent, you plug these things inside the bleeding vein. Okay, so that is a relatively tough question. And this is similar to a question in past exams. So it pays for you to pay special attention to how this can be solved. Okay, let's take this to a scrap page and try to solve it together. So first question, are you dealing with a beam or are you dealing with a bar? I'm talking about the horizontal section. Is it a bar or beam? How can you know it? If that was made of a cheese, how would it deform? Would it deform to become longer, shorter, or would it respond by changing radius of curvature? So I can imagine if these two ends are fixed here, and then I pull that part up, it's going to go through a different, but definitely the radius of curvature will have changed, right? Everyone can visualize it. So therefore, your first conclusion is this is a beam, it's not a bar. Okay, second. The second thing is, I do need to find the internal force at C, but can I do this without finding the reactions? Can I find internal forces without finding the reaction? The answer is no, because I have two options. One option is if I take a free body diagram, an envelope, you as a surgeon, you decide to cut this one and represent it as a free body diagram, or this is left hand side. Or you can choose your envelope like that and isolate it from the universe. This is your second free body diagram. Which one do you take? Well, maybe I would take the right hand side. Why? Because right hand side has a given external force in it, and that makes it solvable. But with the right hand side free body diagram, I need to find that reaction first. Finding that reaction is not difficult. This is a preliminary step. The preliminary step, I assume that this reaction is, I can visualize this would resist this way, but it won't hurt if you take it even upward. That should give you the same number. And this one is resisting upward. So now, to find out, because I decided to take the right hand side free body diagram, I only need By, correct? So By easily can be found by taking net rotation with respect to the A equal to 0. So because A, it has two reactions, right? It's a pin. What type of support is A? That is pin, AX, AY. This one has only one reaction. This is a contact. and two bad guys here, one bad guy here. Maybe you want to kill that. So this is why we take the net rotation with respect to the A. All right, so with that, I have to find out the moment due to 400. What is the moment due to 400 with respect to point A? So you need to find the shortest distance between that fourth line of action and the center of rotation. So that is my line of action. This is the line of action for this force. And the shortest distance of that with this point, that is 1 meter, right? So is this positive or negative? Negative. Minus 400 times 1. And then plus dy multiplied by 5. So from here, you easily find dy is equal to 400 divided by 5, which is 80 Newton. So now I have By. The next decision is I'm going to do a heart surgery. That is, I'm cutting that part of the structure. Right hand side. So let's separate the right hand side and see what the free body diagram looks like. So carefully, because I want to find the internal force at C, let me do the cuts from here. Okay, what is missing here? The missing part is, well, By, I already know that this is equal to 80 Newton. And at C, this is a beam. How many internal forces develop at C? 3. And what are the positive assumptions? The positive assumption for N is like so, N of C. And the positive, because it is the right-hand side free body diagram, the positive V is pointing up, V of C, and the positive bending moment look like that, M of C, correct? All right, is this free body diagram solvable? How many are not? 3 are not, 3 equations. So the easiest way to deal with it, that is, there are 3 bad guys at point C, so I can shoot a bullet and kill 2 of them by taking rotation with respect to point C equal to 0. That would get rid of NCBC, and that M of C, is this positive or negative rotation? Negative minus M of C. And 400, does this make a positive rotation or negative rotation? Negative. Minus 400, what is the arm of rotation? 1. And then, what about 80 Newton? Is this positive or negative rotation? Positive. And what is the arm of rotation? 1 and 1.5, 3.5. So from here, I have M of C is equal to 80 times 3.5 minus 400. So this is important. The interpretation is important. 80 times 3.5.
Negative 1.
Yes, minus 400. That is negative 1,400, right?
No, you were.
Oh, yeah. Yeah, I made a mistake. Sorry, let's do it again.
That's negative 120.
Negative 120, is it?
Yep.
And the unit? The Newton meter. That's bending.
Oh,
Meter. Okay, what does this negative tell me? These negative tell me that At
Going
this point,
that
the
way.
beam is crying. At this point, the radius of curvature is like that. So at point C is a negative bending. The radius of curvature is negative. That's what this means. Okay, next step is to find out the N of C. N of C is equal to 400. That's easy. And that is toward the left. And what is V of C? V of C is negative 80. So here they calculated AX, AY. We don't need that. If we take the right hand side, there's no need to find the reactions at A. We only need reactions at B. So I think we made a mistake somewhere. That 96.
96 is AY. We find B by.
Well, I think we could do the right-hand side 3 by diagram, but the thing is by. Maybe by we calculated wrong.
Or the distance.
The distance. Oh, yes, the point 2 here. We ignore that point 2. This is not 1. That is 1.2. You see? The distance of 400 is not 1. It's 1.2. Because from that line, this is 1.2. That 1.2 make this 96. And 96 make the rest of numbers different. But anyway. So in the exam, just that was the trick. This was the little devil. So the details, devils are in the details.
So in that case, it's like a crime place. Can you draw it in the 3 by diagram?
For the left hand side?
Right hand side, the one that we saw.
Yeah, that's everything was correct except we found that one wrong.
So I mean the bending force is going that way, but it's wrong, right? Our assumption is wrong. It's
Assumption is wrong.
a grind. So can you draw it, redraw it? So I want to
Redraw it?
yeah, I want to see how it's become.
Yeah,
a grind
okay.
base.
So eventually that should look like this one.
So the V is going down instead.
This is M of C. V is going down. N is correct. And that is correct. So look, these two forces tend to rotate my system counterclockwise, and this one cancels this. This is making this counterclockwise. And also we had a force here. Okay. Let's try this problem. You want to find the internal forces at point C, which is 3 meters from the left.
There's no support here, right?
That's a very poor drawing. Let me draw that in a decent way. So that is, you have a cantilever beam.
That was find resultant force and then
You simplify the distributed load first. That's correct. and then at point C, which is 3 meters from here, and the total is, I think, 9. And what is that triangle look like? The triangle has 270 at the beginning, 0 at the end. So this is ABC. This is point B, this is point A, and that was 260, what was it? 270. Okay, you want to find, in another word, you are looking for V of C, N of C, and M of C. That's the final goal. That's what you want to find.
But we have to find the results.
Okay, first thing first, can we do that without finding the reaction?
So there's no.
This was a point.
Well,
Oh, that's one support at point B.
okay, so this is how I do it. Could be a little bit challenging. So I decide not to find the reaction at B. If I don't find the reaction at B, I
Right
need
hand
to take, yes, right hand side. But with the right hand side, you only have a portion of the triangle. You don't have all of the triangle. Does that make sense?
Yeah.
Okay, so tell me, if I want to know exactly how this little triangle looks like, who can help me with that? If that is 270, what is that? This is a similar triangle, right? So that is, I call this X. So X divided by 270, little to the large, is equal to the little to the large. For little, that is 3 take away from 9 is 6, divided by large. Large is 9. So therefore, X is equal to 270 times 6 divided by 9. That is 180. So here, that is 180 Newton per meter, or kilonewton per meter. What is the unit? Yeah, Newton meter. Okay, now with my free body diagram, my free body diagram is, watch this very carefully. This is my right hand side free body diagram. It has a distributed load of 180 here. And what is the span of that free body diagram? This is 6 meters, right? And at this point, what are the internal forces? The internal forces are N of C. Also, that is V of C. And finally, M of C. How do I solve it? Okay, to solve, I'm going to replace the triangle with one resultant. The resultant is area of the triangle. Who can help me with the area of triangle? That's the resultant, or FR. That is equal to 180 times 6 divided by 2. 180 times 6 divided by 2 is 3. .540 Newton.
And we find the position of the knife.
Line of action, also you have to find line of action. From the left-hand side, what is the line of action? 1/3 from the base, that is 2 meters, right? So this is 2 meters from here. Okay, now is this free body diagram solvable? Yes, it has 3 unknowns, we have 3 equations. Starting with net rotation at C equal to 0. So that would get rid of NC, MC, or VC, but MC is in a negative direction, minus MC. And FR makes my system to rotate in a negative direction, minus 540. And what is the arm of rotation? Arm of rotation is 2. And that is all you have. So it's telling me that MC is 1080 negative Newton meter. So that is telling me the beam at this point is crying. And that makes sense because my beam is sad. Or here. And then what about V of C? V of C is equal to 540 Newton. So the shear is positive, the bending is negative. And what about N of C? That is 0. Correct?
Please go to the last, the previous one.
Which one? Okay, I think for today we've done enough. Let's just do a quick summary. So those who arrived late, between now and end of semester, we will be analyzing the beams. Beams compared to the bars or two force members, they are complex. Why they are complex? Because the loadings are more complex. The loadings are not a point load. The loadings are distributed and point load. If there are distributed load, you need to know how to simplify them before finding the reaction. That's the first complication. Second complication is, I assume you know how to identify a beam compared to the bar. Just assume it's made of a deformable structure, and if the radius of curvature changes, that's a beam. The next complication is what happens to the internal forces. Internal forces in beam, in general case, there are 3 internal forces. Axial, responsible for making the beam longer or shorter. Shearing internal force, which does a scissor effect. And the bending moment. The bending moment is responsible for changing radius of curvature. And if you have managed to calculate the reaction, now the question is whether to take the free body diagram on the right hand side, left hand side. You follow the convention of positive assumptions. You put the forces in a positive assumption and then you solve. If you found the numbers to become positive, bending moment positive, that means the beam is deflecting cups up, like laughing. If the assumed convention proves to be wrong, that means at that point the beam is changing radius of curvature in a sad way. Okay, 3 internal forces: bending moment, shear force, N. In some cases, most cases, N is 0. in the cases that we analyze in this unit. But in real life, things are far more complex. All right, any questions? Okay, thank you very much. And let me just finish with attendance, and then you'll be okay. Okay, Ali is here, Tisa here, Daniel here, and here. Sorry, Larry here. Thank you, Larry. Jackie was here, John here, and Rachan here. Okay, thank you very much. And I look forward to see you Thursday.
All right, see you.
Thank you. See you.
I'll have to reschedule the test because I missed it yesterday.
You missed the test yesterday.
No,
Thank you. Thank you.
See you, sir.
it's like we can schedule it any of your protein.
Let me see. You sent me medical certificate, did you? Okay. So, all right. So, when can you take it?
Any of the protein next week.
Next week?
Yeah.
Can we do this next week after the same class?
It's Monday.
Tuesday.
Tuesday. This Wednesday.
Yeah. Once we finish that, you come with me over there. I give you a test to see. All right?
Okay, sure.
Yeah.
So it's like next Tuesday, 12:30. All right, sure. Okay. Thank you, Mr.
Thank you. Thank you.
Have a good day. Thank you.
Thank you. Thank you.